A much more interesting distribution than the uniform distribution is the exponential. It has many more applications and can be used to estimate our discrete random variable, the Poisson. The exponential distribution describes a wide range of situations. It can provide the probability of service times for customers, like how long it takes to fill your car with gas or have a haircut. It will calculate the probability for the times between arrivals at a toll booth on a highway or between accidents on the same road. The exponential is the cousin of the Poisson distribution, but the difference is important. First, the Poisson is a discrete random variable where time, a continuous variable, is artificially broken into discrete pieces. We saw that the number of occurrences of an event in a given time interval follows the Poisson distribution. For example, the telephone just rang. How long will it be until it rings again? We are measuring length of time of the interval, exponential, not events during an interval, Poisson. Classic Poisson distribution questions are, how many people will arrive at my checkout window in the next hour? Classic exponential distribution questions are, how long will it be until the next person arrives? The formula for the exponential is probability of x equal 1 divided by mu times e raised to the negative x divided by mu. We see immediately the similarity between the exponential formula and the Poisson formula. Both probability density functions are based upon the relationship between time and exponential growth or decay. The e in the formula is a constant with the approximate value of 2.71828 and is based on the natural logarithmic exponential growth formula. When people say that something has grown exponentially, this is what they're talking about. Although almost never do they really know what they're saying. Growing exponentially has almost become just an expression. An example of the exponential and Poisson will make clear the difference between the two. It will also show the interesting applications that they have. Suppose that historically, 10 customers arrive at the checkout line each hour. Remember that this is still probability, so we have to be told these historic values. We see this as a Poisson probability problem. We can put this information into the Poisson probability density function and get a general formula that will calculate the probability of any specific number of customers arriving in the next hour. F of x equals 10 to the x power e to the minus 10 divided by x factorial. This formula is for any value of the random variable we choose, and so the x is put into the formula. As an example, the probability of 15 people arriving at the checkout counter in the next hour would be probability x equal 15, 10 to the 15th power, e to the 10th power, all divided by 15 factorial. Here we have inserted 15 and calculate the probability that in the next hour, 15 people will arrive. The answer is 0.061. Of course, if we keep the same historical facts, but are interested in the service time a person spends at the counter, we would use the exponential distribution. The exponential probability function for any value of x, the random variable, for this particular checkout counter is f of x equals 1 divided by 0.1, e raised to the minus x divided by 0.1, equals 10e raised to the minus 10x power. Okay? To calculate mu, the historical average service time, we simply divide the number of people, 10, into the time period, 1 hour, and have mu equal to 0.1. Historically, people spend 0.1 of an hour at the checkout counter, or 6 minutes. This explains the 0.1 in the formula. If we wanted to know the probability that a person would spend 9 minutes or less checking out, we use this formula. First, we convert to the same time units, which are parts of 1 hour. 9 minutes is 0.15 of an hour. Next, we note that we are asking for a range of values. This is always the case for a continuous random variable. We write the probability question as the probability of x equal to or less than x naught equal 1 minus 10 times e raised to the 10x power. Okay? The probability that a customer will spend 9 minutes or less checking out is 0.7769. We find this by looking at the formula probability x equal to or less than 0.5 equals 1 minus e raised to the minus 10 times 0.15. That equals 0.7769. We see that we have a high probability of getting out in less than 9 minutes and a tiny probability of having 15 customers arrive in the next hour. Now we know why we see those clocks at the drive-in windows. They are developing historical data to calculate the probabilities that we have just been doing. These can be very helpful in making decisions on staffing, back office flow of work, and any number of other decisions that affect the business and their customers.